Okay guys, I am recording this video for the second time because apparently the audio did not work the first time. So if you've already tried to watch this, sorry. Okay, so by the end of today's lesson, you will know what an inequality is, and you can solve it using graphing technology. And I should also state, and you can express your answer in interval notation. That is important as well for this lesson. Okay, so what is an inequality? Well, inequality means things are unequal. So normally, or not normally, but in the past, we would have solved something like when is x squared equal to 4? And then we would maybe graph this or use various methods. So in this case, we could use inverse operations. So we could say, okay, let's take the square root of both sides, and x squared is equal to 4 when x is equal to plus or minus 2, because we could do positive 2 squared and get 4, and we could do negative 2 squared and get 4. So that would be solving an equation. But what about when we solve an inequality? Because now we don't want to know when does x squared equal 4. We want to know any time when x squared is greater than or equal to 4. So what we're going to focus on in this class is using technology to answer these questions, to give us those visuals, and then eventually in our next lesson, we'll move on to how do we do this algebraically, how can we do this without technology. So using technology, we would graph x squared on a Cartesian. So if this is our parent quadratic, it has its vertex here at 0, 0, and we know that it looks something like this and something like this, and when x is 1, y is 1, when x is 2, y is 4, or y or f at x, and when x is negative 1, f at x is positive 1, and when x is negative 2, f at x is positive 4. So here we have these two coordinates at 2 and 4, and over here at negative 2 and 4. And we want to know for all x values, any x values that provide a function value when this entire function is greater than or equal to 4. Well, if we were to draw some sort of horizontal line here at, say, f at x is 4, the places where this function is greater than 4 are anywhere here and anywhere here. So we could state our solution as intervals. So we could say, well, x squared is greater than or equal to 4 when, over here, x is greater than or equal to 2, and also, or and, when x is less than or equal to negative 2. It happens over two intervals. It happens anywhere from here at negative 2, and for any other value we could possibly sub in that is less than negative 2 would give back a function value that's greater than 4. And for any value that we sub in, including 2, and anything greater than that, is again going to give a function value back that's greater than 4. If we sub in anything in between there, we are going to get a function value that is less than that red line, which is 4. So that's how we could write it using what we call inequality notation. The other thing I want to show you is that Desmos is really good at showing you the answer for inequalities. So here I have my graph of x squared, and when I actually type x squared is when is x squared greater than 4, or sorry, I should say greater than or equal to 4, it gives me this graph. And I'm actually going to show you on Desmos. If I go to Desmos, and we're going to use that one later, but if I say when is x squared greater than 4, let's keep what the question said, greater than or equal to 4, it looks like this. So what this tells me is that the values where x squared is greater than or equal to 4 are anything from negative 2, it tells me the point, until all the way to negative infinity, or anything less than negative 2, and anything from positive 2 all the way to positive infinity. Now, if I change this sign, notice how these lines are solid. That means it is inclusive of negative 2 and positive 2. Those values also will make it, because it's not asking just when is it greater than 4, it's asking greater than or equal to. And at exactly negative 2 and positive 2, it's equal to 4. If we change this and say just when is it greater than 4, notice how these lines are dotted, and that means not inclusive of this point. So less than negative 2 but not inclusive of negative 2, and greater than 2 but not inclusive of 2. Okay? And we're going to look at different ways to express that as well. So because these lines are solid on Desmos, I know it is inclusive of that point, which is why I use my less than and actually equal to negative 2. So for that question, these were our two solutions, and this here is actually called your inequality notation. So for the answer to that question, we could say, well, x squared is going to be greater than or equal to 4 when x is less than or equal to negative 2, and when x is greater than or equal to positive 2. So that's your inequality notation. I'm going to show you interval notation, and this is actually the notation that I would prefer that you use for this course, and probably the one you'll see moving forward depending where you're going with your math and post-secondary calculus, things like that. So if you were going to do this on a number line, there's a couple things to keep in mind. That a closed circle on a number line means that it is inclusive of the point, and an open circle on a number line means that it is not inclusive of that point. And so if we were representing this inequality, we would say from negative 2 and inclusive of negative 2, from positive 2 and inclusive of positive 2, and then just because I find it really hard to draw a straight line on here, I'm going to use my arrow tool and say from positive 2 all the way to positive infinity, and from negative 2 all the way to negative infinity, and like I said, inclusive of those points, negative 2 and positive 2. If it was not inclusive of positive 2, it would be an open circle, and then we would have our line drawn. Okay? We'll look at some examples today where that's the case. So this is the exact same answer represented on a number line, represented using inequality notation, and then I'm going to introduce what might be new to you, which is called interval notation. So similarly, we need to lay down some ground rules to use interval notation. So when we're using interval notation, round brackets means not inclusive of that point. Okay, so it's kind of like when we do our number line, open circles means not inclusive, closed circles means inclusive. When we're using interval notation, round brackets means not inclusive, square brackets means inclusive, and positive and negative infinity are never inclusive because they're not real numbers. They're just up until forever and ever in both directions, but they're not it's not an actual number, so we can't say that that specific number is included in the interval. So I'll show you what we mean by that. So if we were talking about this interval here, so from or anything less than or equal to negative 2 and anything greater than or equal to positive 2, really what the interval here is anything from negative infinity all the way up to negative 2, and anything from positive 2 all the way up to positive infinity. So to write this using interval notation, we would say from negative infinity, but not inclusive of negative infinity, so we're using our round bracket, all the way up to negative 2, but yes, inclusive of negative 2, and again, from positive 2 and inclusive of positive 2 up until positive infinity and not inclusive of positive infinity. This is just it's a symbol, it's a union symbol, and we can just think of it as and. So from negative infinity, not inclusive of negative infinity, to negative 2, inclusive of negative 2, and from positive 2, inclusive of positive 2, up to positive infinity, not inclusive of positive infinity. So this is the interval, or this is the notation that I would prefer you to use, and the one that I will be using to present these solutions moving forward. So right now, I would recommend that you pause this video and that you try this idea of interval notation on your own. And so it says represent each interval below using a different method, but I'm going to say using two other methods. And so for the first one, it's given to you in inequality notation. I would like you to represent this in interval notation and number line notation. The second one is given to you in interval, so you're going to represent inequality and number, and then you have your number line, you're going to represent in inequality and interval. So I'm going to pause the video, and I want you to do the same, and then you can come back when you have completed these to check your work. Okay, so here are the answers for that one. So this interval reads when x is greater than or equal to -3, so greater than meaning moving this way, or equal to -3, but when x is less than +5, but not inclusive of +5. So this is what that interval would look like on a number line. We're talking greater than or equal to -3, less than but not equal to 5. So this is an interval between 2 points, and using our interval notation, we just represent it as from -3 to 5, inclusive of -3, and not inclusive of 5. This one here is represented already in interval notation, and this is 2 different intervals. So this is something that's happening kind of like that first question where, it's happening here and it's also happening here. It's possible there's more than one interval. So this is from the interval -infinity, not inclusive of -infinity, up until 2 and inclusive of 2. So anything from -infinity all the way up to 2 and inclusive of 2, so colored in. And then again, pause and from +4, but not inclusive of +4, round bracket, up until +infinity. And so we could represent it on a number line, or we could say when x is less than or equal to 2, and when x is just greater than 4, but not equal to 4. And then again, the last one is between 2 points, and we have from -2 up to +3, not inclusive of -2, but inclusive of +3. So that would be the interval between those 2 points using interval notation, and this is the one where people typically see the value in interval notation versus the inequality notation, because then we have to be able to recognize, okay, so x is greater than -2, but not equal to -2, and x is less than +3 and can be equal to +3. All right, so that is just practicing that interval notation. So the next thing we're going to do is look at an example. So we want to know for what values of x will 0.5x plus 3 be less than 5x minus 6. So I want you to take a second and think about what this is actually asking you for. What does that inequality mean? We don't want to know when these two things are equal because they're unequal. We want to know when this is less than that. Okay, so take a minute, think about that. Okay, so hopefully you had a minute to think about what this is actually asking. So these are both linear functions, and this is a linear equation with, well, really it could be 1 over 2x. So it has a y-intercept of 3, and then it goes up 1 over 2, up 1 over 2. And this is a y-intercept of -6, and it goes up 5 over 1. And what we want to know is what x values will make this function less than this function. So I'm going to show you the graph of these two functions, and here we have a linear function with a y-intercept of +3. So hopefully we know that that's this one here, the green line. So this is the green line, and this one over here, the y-intercept of -6, is going to be our purple line. And really what this is asking us is what values of x will green be less than purple, or in other words, we could think about it, will green be below purple? So because these are two linear equations, they will always have a point of intersection. All linear functions will intersect unless they are parallel, meaning unless they have the same slope, in which case they're running in the same at the same slope forever and ever, so they'll never cross. But if they don't have the same slope, even if it's off just by a little bit, they will always intercept. So this is our point of intersection here. So what always happens, a little bit of a throwback to grade 9, grade 10, anytime two linear functions intercept is one function goes from being on top of the other to being below the other. Okay, so green went from being on top to being below. Purple went from being below to being on top. So we want to know what values of x make green be below less than purple. Well, green is below purple after their point of intersection. So anytime x is greater than 2, okay, anytime we move this way, green is less than purple. And this is not asking when they are equal to each other. That would be their point of intersection. It's just less than. So to express this, we would say, well, 0.5x plus 3 is less than, not equal to, just less than 5x minus 6 when, I'm just going to jump right to when x is greater than positive 2 and not greater than or equal to, because at that point the functions are equal. We're not interested to when they are equal. We're only interested when green is less than purple. So of course things are going to get trickier than just two linear functions and a point of intersection. So now we have this here. We want to know when is this quadratic, which is the green curve that we see, less than or equal to this time. We don't need that. Less than or equal to this linear function, which is purple. Okay, when is the green below purple? So again, what we really want to pay close attention to are those points of intersection. They intersect here at an x value of -1. So anytime two functions intersect, one function goes from being below to now being on top, or from being on top to now being below. And so down here, they also intersect. And again, we went from purple being on top to all of a sudden now purple is below. That is quite literally what the point of intersection means. And it's hard to see here, but that happens at -5. So we want to know any times, any values of x where green, I don't know how we lost our n there, maybe I never wrote it, where green is below, right, or less than purple, but not just below or equal to this time. So when is green below? Well, as soon as we move past -1, right, as soon as we get greater than -1, green is below purple. Purple has higher function values than green. And these functions, this is the full graph. This is a straight line. It's not turning back around. This is a quadratic. It's not turning back around. So I can assume that this is from now until forever. So one of the locations is when, I'm going to just write it down here, x is greater than or equal to -1, right? Because it's equal to, because I also want to know when these functions might be equal. And the other time where green is below purple is any time when x is less than. If I sub in any value that's less than -5, so if I sub in -6, -7, anytime I sub that in, green is always going to be below purple. And that was at -5. So, or when x is less than or equal to -5. Now that is that interval, the inequality notation. I would prefer to see when x is from -infinity up until -5, inclusive of -5, and from -1, inclusive of -1, all the way to positive infinity. Those are the two intervals where green is less than or equal to purple. We're including the x value at the point of intersections because that's this part. That's when they are equal to. Okay? So that's one way we could solve these using technology. We have two different polynomials. We want to know when is one greater than or less than, equal to, etc., than the other. However, there is a little bit of an easier approach. So what we could do, and I like to start with this approach so that we recognize what this is really asking us for. Okay, we're analyzing point of intersections. We're analyzing when is one function above or below the other on either side of any point of intersection. But we could make this easier. So if we wanted, just like if I asked you to solve this, if this was not here, if this just said equal to, you would bring everything to one side so that you have 0 on this side and one single polynomial on this side, and then you'd factor it and you'd be able to solve. So we want to do something similar here. Whoop. We want to isolate all of the, combine the polynomials on one side and isolate 0 on the other. So we want to take away 5x on this side, and we want to take away 4 on this side. And when we do that, we have to take away 5x on this side and take away 4 on this side. So we're left with -2x squared minus 7x minus 5x minus 6 minus 4. And on the other side, we're left with 0. So we want to know when is all of this less than or equal to 0. So we can simplify this. We can say -2x squared minus 12x minus 10. Now we've created a new degree 2 polynomial. So we want to know, when is this polynomial less than or equal to 0? So again, because we're using technology today, we can just put this polynomial into Desmos, which I've already done. Let's get rid of that. Negative 2x squared minus 12x minus 10. When is this less than or equal to 0? Well, 0 now is here. This is our function value of 0. This is a function value of 2, 4, 6, etc. So the places where it's less than 0 is from here and down, meaning from this x point and anything below it, and from here down, meaning this x value and anything greater than it. If I sub in any x value that's greater than negative 1, I'm going to get back a function value that's very, very negative. And if I sub in any x value that's less than negative 5, and notice how the solutions here are the exact same as the solutions when we were looking at that point of intersection, when we had it as two separate polynomials. So the answers are the exact same, from negative infinity up until negative 5, and again from negative 1 up until positive infinity. That's literally what we see here. From negative infinity all the way up until negative 5, it's less than 0. And again, from negative 1 all the way to positive infinity, it's less than 0. So this is the method we're going to use, is understanding what the question is asking really. But when we get our answer, or how we get our answer, is going to be to isolate all of the, or both of the polynomials to one side of the inequality as a single polynomial and leave the other side isolated to 0. Okay? So for the practice questions, just know we're just going to use Desmos for your graphing calculator, and make sure you algebraically rearrange each inequality so that what you're really asking is when the function is above or below 0. That's always going to make your life a lot easier to read the graph. So you're not having to look at those point of intersections, but recognizing that the point of intersections of two different functions become the x-intercepts when you rearrange the inequality and isolate both or combine both polynomials to one single polynomial on the other side. Okay, so we're going to continually be doing that rearrange approach, and the x-intercepts become the boundaries between those intervals. Okay, so there's some practice questions. The exit ticket primarily focuses on this stuff, on being able to represent answers in the various notations, just because this is usually the part that we struggle with. And then in the next lesson, we will look at how we can do this without using any graphing capabilities.